Welcome back to a new exercise. This time we're going to mix a little bit of accelerated motion with uniform motion, so there will be different sets of equations for different parts of the exercise. So let's have a look. An athlete swims, starting from rest, with an acceleration of 0.5 meters per second squared for 6 seconds, after which she continues at a constant speed, reaching the other side of the pool. Find the length of the swimming pool reached after a total of 17 seconds. Alright, so first step as usual, we have to read the exercise again, but this time identifying the keywords or key terms that can give us a lot of the information that we need. First part is we identify that the initial velocity is given here in the term of from rest. The idea that the swimmer starts from rest means that the initial velocity is 0, so we can set v0 is 0 in this part. We're also given the acceleration and the time for this part of the exercise. Then we have the second part, which starts with the comma and the after. So this combination, the comma and the word after, sometimes is the word then, implies that here's when the second part of the exercise will start. And of course the first part will finish. So after this point, she continues at a constant speed and will reach the other side of the pool. The question is, find the length of the swimming pool. We also have the total time. The next step is we draw a cartoon for which we start by selecting or choosing our coordinates. As usual, we start with our line that will represent the x-axis. Somewhere here we have the origin of the coordinate system, which is the point where the swimming pool starts, and the swimmer will go to some distance that we can simply call L. L is the length of the swimming pool. According to the exercise, there are two parts. First, the swimmer goes in an accelerated motion, and at some point, somewhere here, let's call that point D, that means distance D from the origin, she will switch from acceleration to non-acceleration, meaning the velocity here will remain constant, and at some point she will reach the other side of the swimming pool. In order to make clear that there are two parts of this for this exercise, I will even use two different colors for the two parts, the two situations. So we have here some acceleration A. We also know the initial velocity here was 0 because it says here that she starts from rest. She will swim with this acceleration, increasing her speed, and at some point here, some time t, she will switch from acceleration to non-acceleration. So at some point when she reaches this point that we simply call D, she will start moving with a constant velocity that we can just call v, and she will continue with this constant speed all the way up to this point. For the total travel time will be 17 seconds. Let us start with the first part of the exercise. That means when the motion is accelerated, the position of the swimmer, x, will be the initial coordinate plus the initial velocity times the time plus 1/2 of the acceleration times t squared. The initial position is 0 because we selected the coordinates in that way, so we have done several times already. The initial velocity is also 0, so this term also cancels, and we're only left with the final term, 1/2 of at squared. So this is expression here, this is x. This expression here is valid at any time, before t, of course, switches from acceleration to uniform motion. We call D the point where this change happens, and we know that this happens after 6 seconds. In other words, when x is equal to D, we have 1/2 of at squared where t is equal to 6. So we can write this as 1/2 times the acceleration, which is 1/2 meters per second square, times the time, which is 6 seconds square. As usual, the second square will cancel, and since we're looking for a position, we're going to get the result in meters as expected. We can plug these numbers in the calculator. Let me move it a little bit to the side. We have 0.5 times 0.5 times 6 square, which is 9. Therefore, D is equal to 9 meters. And this is D. So we know the distance from the initial part, from one side of the swimming pool, where the swimmer will switch from acceleration to uniform motion. We can continue then on the other side for the second part of the exercise. Here the motion is uniform. Therefore, we use the expression for the position in uniform motion, which is initial position plus v times t. Here I want to make a few remarks. The x0 that I wrote here has nothing to do with the x0 on the left. Okay? So even though I'm using the same symbol, they represent different things, because in the color here on the left, in this greenish color, represents what happens in the first part of the exercise, whereas this brownish here represents what happens in the second part. So this x0 has nothing to do with that one. That's why I'm even using different colors. The initial position corresponds to the final position of the first part. In other words, this x0 here is d, because here is when this motion starts. So this is x0 is equal to d. Plus v, we don't know what the velocity is. In fact, we need to find that. And the same applies to t. Even though I am using the letter t here in the same way as I used it before, they represent different quantities. This is the t starting from this point. Okay? So this t represents for how long this motion occurs, but is only valid after the swimmer went through point D. So once we have that clear, we can just call it T. So this is the position of the swimmer on the second part of the exercise at any time. We would like the swimmer to reach point L, which is the other side of the swimming pool, for which, let's see, we don't know the time explicitly, but we know that the total time is 17 seconds, and we know that for the first part she took 6 seconds. Therefore, we can immediately find that the second part of the exercise takes a time of 11 seconds, because 11 plus 6 will be equal to 17. And this is the number that we would like to plug here as t. The problem is that we don't know v. So how do we find v? V is constant, is the same over all the section beyond D, between D and L, but we don't know what that is. That is not given. However, we can find it from the first part of the exercise, because we know the initial velocity and we know the acceleration. We also know the time. So basically we have all the information to find that. So let's switch back for a minute to the first part of the exercise. So I switch back to my greenish color. I will just draw a line here, and I will write this expression that we have to find the velocity, which is the initial velocity plus acceleration times time. Initial velocity, we know already that that was 0 because she started from rest. So this is simply a t. Now we would like to find the velocity after 6 seconds. So we simply plug these numbers. The acceleration was 0.5 meters per second square. Put some parentheses there just for clarity. Times the time, which is 6 seconds. So seconds will cancel, and we get the result in meters per second as expected, because this is a velocity. So 0.5 times 6, that is just 3. So this is the velocity of the swimmer at this point, when she is at x equal d, which is the same as saying after 6 seconds. Great, so we know this velocity now, and now we can plug this quantity here, because that final velocity of the first part of the exercise corresponds to the velocity of the second part of the exercise, which is all the time the same because it's uniform. Great, so we can continue here and plug the numbers. D is 9 meters, as we found before, plus the velocity, which we just got it to be 3 meters per second, times the time. Which time? This is the time that it takes to go from D all the way to L, which we found to be 11 seconds. So this is 11 seconds. We can do the multiplication. 3 times 11 is 33 meters, because again, seconds cancel. And this gives us a total of 42 meters for x equal L. So what I have done here, when I plug the value 11 seconds, I am saying that x is equal to L, because this is the other side of the pool. Here we have it. The length of the pool is 42 meters. The important points, or the important take-home messages here are: notice that the exercise has two parts. In one part, for this case, there is acceleration. For the second part, there is no acceleration. The information from the first part corresponds to the initial information of the second part. And this is how we derive all the relevant quantities, and we were able to find the length of the swimming pool.